Well, all right, everybody. I think I'm going to go ahead and get started. Welcome, and this is week 8. We're basically at the halfway mark of the whole semester, just like that. So, I hope that things are going well for all of you guys, and I know I'm keeping you kind of busy. There's been a lot of work. It will taper off, certainly with respect to the homework, once we get through this week. Next week will be much lighter on that score, but that's partially because of something else. I'm going to try to put on my screen if I can. We have an exam coming up, so I just want to talk about that for a quick minute. Get everybody oriented. We had our first midterm on September 19th, and so our second midterm is on October 19th, exactly 1 month later. And that is next week on Thursday. So if this thing will crank up here, I'm hopefully going to be able to show you in a second. There it is. This is the Canvas page, right? So the usual view of it here, the front page. So let me just point out that in the files section of this Canvas page, there is a folder that is called Midterm 2 Resources. Okay, so I'm just going to open that up really quick and just show you. There's a bunch of things in here. It's the same thing I did for the first midterm. And I told you at that time that I always have like way too much stuff. I would never expect everybody to look at everything that's in here. It's kind of going to be up to you. I will point out that the bottom 4, there's 8 things in here. The bottom 4 things are actually 2 different sample midterms. So I decided to go crazy on that this time and give you 2 sample midterms. You don't have to do them both. You don't even have to do one of them really. But honestly, if I was only going to be able to do one thing to prepare for the exam, I probably would do a sample midterm. I would prioritize that because it'll give you an idea of like what kinds of questions I might ask, how long it's going to be, sort of the breakdown of the topics and all of that kind of stuff. So I would recommend doing at least one of the sample midterms. And if you do one of them and it's like, this is a little shaky, then you might think about doing the second one as well. As you can see, I did put the solutions to them there. The only way I've differentiated them is the one set is in all caps. The file name is in all caps. The other one is just lowercase letters here. So anyway, there's a couple of sample midterms for you to practice. There's also a review session. So these 2 documents are some review session problems and then also solutions to those review session problems. But I should point out, just like with the first midterm, if we go to the pages section of Canvas, we're going to find video for that second midterm review session. So I've got a 90-minute video followed by 38 minutes here. So approximately 2 hours for me to go through those review session problems. So if you don't like to just read my solutions, you'd rather listen to me talking about the problems, you're certainly encouraged to take a look at that. I don't think I did the problems quite in the same order that they appear on the sheet, but they're all in there. You just have to be willing to patiently kind of go through that. But yeah, so you can choose to watch the video if you'd like. Honestly, if you're gonna make time for the review session, I would probably do that kind of on the earlier side because it should get your mind trained a little bit onto like what are the topics that I need to be thinking about for this test, right? So checking out those review session videos might not be a bad idea if you have time for it. If you don't have time for it, then definitely focus more on the actual folder here. You can, as I said, just read the solutions and take the review session problems and their solutions and kind of work with them that way too. So it's kind of whichever. I just know some people learn better by reading. Some people prefer to listen. It's however is best for you. You have your option on that. And then finally, just at the top here is just the actual review folder. It's review packet itself. So let me just actually open this one up. So again, this tells us the date, Thursday, October 19th. Obviously, we'll be here. I talk a little bit about the review sessions. I'm going to announce some office hours later for that. Of course, I'm definitely going to have office hours. And this is what maybe you wanted to know about is what is it going to cover? we've already finished all of chapter 4, and you can see that that's a big part here, 4.1 through 4.10, with the exception of 4.7, which is the one section that we skipped, but we did everything else in chapter 4. So currently, we are working through chapter 5. There's just 3 sections in chapter 5, and I'm planning to more or less finish at least the lecture material on that today. And then section 6.1, I'm planning to cover on Thursday. So we'll hopefully have all of these sections done by this Thursday. You'll still have a whole nother week to kind of get on top of that stuff. And so that's what it's going to cover. The rest of this packet is, as usual, just kind of an overview. It's not a bad thing to just kind of go through this, glance through it. What are the things from chapter 4 I need to review? Chapter 5 and 6 are much shorter, as you can see. And then a list of things to be able to do. I've got a big long bullet point list here. I would go through that and kind of use it like a checklist. If you come to something on the list that you're like, ooh, I don't remember that, or I don't quite know what he's talking about, then that's a great thing to ask me during office hours, or talk with a friend about it, or whatever, right? To just kind of make sure you know what that's all about. So that's a pretty long list here. And obviously the sample midterm is then going to line up with these bullet points. So, you can kind of use this as a guide for that too. Just a little bit of advice. I suggest starting with group work number 6 if you're going to review the group works, which I think some people like to do that too, and it's not a bad idea either. You can start with group work number 6. We've done 6 and 7. Today we're going to do number 8, and I'm hoping on Thursday I'll have time to do number 9. So there'll just be 4 group works for this section. I'll take care of that. And then you don't really need any more problems that I'm already giving you in the sample test and so on, but just in case somebody is like really wanting to go above and beyond, there are some practice problems in here as well. So quite a few of them, actually. I guess 9 of them only. Okay, so anyway, so those would just be if you ran out of other things to study, or you just were looking at some people, I think, decide that there's certain topics they need to focus on, which is good. If you have certain topics that you want to practice extra on, you can obviously thumb through these problems and look for problems that are like what you're looking for, right? So you can also do it that way. Does anyone have any questions about this? This thing's up here, it's on Canvas. It's just going to be totally wide open the whole time. Answers to everything are already here. You've got the video to watch. There's plenty to do. So the last homework that you'll have to do will be due on Sunday. So the test is Thursday. So you'll have, once we're done with that last homework assignment, which will just be section 6.1, then you'll have 4 days with next week, there won't be any homework at all. Obviously, I'm just going to have you working on this stuff and getting ready for the test. Okay, sound like a game plan? Okay, fantastic. Well, I'll turn this off for the time being then. Just wanted to get that on everybody's radar. We definitely still have some time before we get to that. What I've done on the board here in my recap is just some of the stuff from 5.1, right? So at the start of chapter 5, remember chapter 5 is all about trying to put geometry ideas into a vector space. Chapter 4 was just so dry with just algebra, right? It was just like addition and scalar multiplication and just everything we can do with that. And so we talked about vector spaces and subspaces and basis and dimension, all those kind of things, right? Well, as I mentioned last time, mathematicians never lose an opportunity to try to infuse something from their familiar experience in our three-dimensional world into these more abstract types of structures. So the whole idea behind an inner product space is to take a vector space and equip it with some geometric ideas, okay? And I've got some of them here. We talked about the norm, which is really just the length of a vector, if we want to use really casual language for that, right? The length of a vector, just with these double absolute value bars, right? And then the angle between two vectors, that's another geometry idea, right? And it also involves you know, the norm of the vectors involved as well as the inner product itself. If you ever kind of lose touch with what this is all about, remember guys that inner products are really just like generalized dot products. If you remember your dot product from Calc 3, right? Inner products are really just attempting to replicate that dot product idea, but in any vector space. So you might not be working with just vectors with slots in R3 anymore, but all of these other examples we've looked at, such as matrices, polynomials, functions, and so on. And in the homework that you're doing for tonight, there's examples of that, right? You're practicing these ideas, finding the angle between two functions. It seems like a weird thing to do, but we can actually make sense of that now if we have this inner product. It's very important that we know what an inner product is. So there are, these 4 axioms here. These are the rules of an inner product space. And I do want you to know all of these. And although it looks like it's 4 rules, I have to be a little bit flexible with that, because the first axiom actually sort of has 2 parts to it. And actually both parts are really important. So the first one is if you take the inner product of a vector with itself, remember you have to get a number, right? Dot product, if you take the dot product of 2 vectors, you always get a number. So we're talking about a number here, right? But that number, when you apply the vector to itself, has to be not negative, right? Has to be at least 0. And the second part of it, which I put in the parentheses here, but it's just as important, is that the only way that this value can be equal to 0 is if we're talking about the 0 vector itself. Okay, so it's a 2-parter, and I'm kind of emphasizing it a little bit because a lot of times when these inner product axioms fail, which some of the homework's asking you to check these axioms, right? If those axioms fail, it's often the first axiom. I mean, I'm not going to say always, but it's often the first axiom that does not hold, right? And so we want to really be good with working with that axiom. Okay. Questions so far? Yeah, Matt.
So for it to be an inner product, it has to pass all 4.
Has to pass all 4. That's right. If any one of these 4 axioms fails, it's game over, right? It's not an inner product, and we're done. So I usually like to check this first one first because, as I said, it's the one that sometimes can be more problematic. And so if I find out that the first one doesn't hold, then I'm kind of in good shape. I don't have to keep worrying about the rest of it here. Yeah. Guys, it's really important because this is kind of some weird notation that we keep very clear when we're looking at a number versus a vector, what these expressions are really meaning. So try to draw arrows. You notice how I'm pretty solid on that. I always try to draw arrows on top of anything that's a vector, right? To keep it clear in my head what things are vectors and what things are numbers, right? The inner product itself is actually a number, okay? But that includes these angled brackets. Also, be very careful to draw those angled brackets so that they don't get confused with parentheses, because the minute you start to see this as if it's 2 parentheses, then it starts to look like it's somehow like a vector in R2, which it isn't, right? It's a number, right? This thing is a number. So we don't want to get confused. I will be honest, I don't think it's the best notation the math world ever came up with for something, because it does kind of look like it's got slots, like it's a vector or something. But it's what we have. It's what everybody uses. Kind of just have to live with that. Okay. So anyway, I just want to caution you. Sometimes I think that from my past experience with this class, that where people can sometimes get a little bit mixed up is just the notation, right? So keeping vectors straight from numbers and keeping this inner product straight from like a point. They're 2 different things. Okay. Is everybody good? So far, so good. This is just a summary. I always like to start, especially on a Tuesday after a long weekend. I like to kind of go slow and remind ourselves where we were from before. Okay. So these axioms all have to be true. By the way, the second, third, and fourth axioms allow you to sort of manipulate these inner product notations. You can switch the order. You can switch the order of the two slots. You can pull constants out. That's the third axiom, right? You can pull this C out in front. You can split up plus signs into separate pieces, right? So x1 plus x2, break that apart, yeah? So these are the rules of inner products that you either are verifying, if that's what they're asking you to do, or that you are using if you have something that you already know is an inner product, you see. Notice on the third and fourth axiom, all of the action is happening in the first position. The constant is in the first slot. I hesitate to use the word slot here, but I'll do that. I think you know what I mean. The constant is in the first slot. The plus sign is in the first slot, yeah? But actually, because of axiom 2, which allows me to switch the order of the two slots, I could have done the same thing with the second slot. If I want to bust a constant out of the second slot, I can do it because effectively I would just have to switch it to the first slot, then bust it out, and then switch it back again. Actually, you have to do that on some of those homework problems at the very end of the assignment for tonight. So you'll get a chance to actually write it down for yourself and see how it looks as you're working on that. Okay. So yeah, so a couple of big things we need to get to in a second, Jared. A couple of big things we need to be learning in this section. One is we need to be practicing these axioms, checking are they true or are they false, right? Writing it up. How do you write it up? What's it look like? Yeah. And then the second thing is we need to be using the inner product concept to answer geometry problems that might come along as well, because that's the whole point of it, right? That's the whole purpose of this. So most of the homework for tonight is working on those two things, either practicing the axioms or using the axioms to then do some kind of a geometry application. Yeah. So Jared, you had a question for me.
For axiom number 3,
Yeah.
If x and y like both have a constant and you take it out, the constants would be multiplied, like if they both had a 2.
Correct. So if you have constants in front of both slots, you can imagine factoring each of them out, which ultimately leads to a multiplication of those constants. Great point, and that does come up as we will see in the homework, for example. Any other questions so far? Well, I tell you what, I can see that there's at least 3 questions, which are these problems that are on the board over here. I think I'd like to talk about the homework right now. So because this homework is relevant to exactly what's on the board right now. So why don't we take just a few minutes and look at some of these problems from tonight's homework. This is from 5.1, and this is some good practice. Some of these problems, by the way, are just straight out of the video that you watched about a week ago. I had you watch, I think, not this weekend, but the previous weekend, I had you watch a video. This is for extra credit, you might remember. So you'll recognize some of these problems, I think, from there. Let me look at number 4 from tonight's assignment. This one is a geometry application. F of x equals the sine of x. And then g of x is equal to 2 cosine of x plus 4. And then they give you the inner product formula that they want you to use. So guys, they have to give you the inner product formula. If they don't give you an inner product formula to work with, then you're kind of like, that's like kind of, I don't know, being in a canoe without a paddle. It's like, I don't know where to go. I don't know how to do anything, right? So you have to be given this formula. So they give you the formula, which is from this section of the text. Let me write it down. So this is given. This is not something we have to explain or understand. It's just a given expression. And what it is the integral of f of x times g of x dx, right? And the limits of integration can be anything we want. Okay, in this particular problem, they give you the interval that they want you to focus on, which is from 0 to pi over 2. So in the examples of inner products, this is like your second most important example. Behind the dot product being, of course, the classic go-to example of an inner product. If somebody asked you what would be the second most important inner product that mathematicians use, this is the one you would say, right? And this, of course, is not dealing with vectors in Rn, but rather with functions. Okay, so we're in a totally different universe now, right? That's the whole idea. V could be any vector space. Doesn't have to be one of the standard Rn's, right? It could be any vector space. So in this case, the vectors that we're looking at, as you can see, they are functions. They are functions. And so I can evaluate the inner product of those two functions. How do I know that this is a valid inner product? How do I know that it satisfies all of these four axioms? Oh, it's because we watched the video, right? In that video, I showed all of these axioms once and for all, right? You only have to check something once, right? Then it's true like forever. So we already know that this is a valid inner product. We don't have to ponder that or worry about that. Besides which, they shouldn't be giving you something that's a valid inner product. If this was not a valid inner product, we couldn't really do this question. So it better be valid. Right, okay, so sorry, let's see, what do they want us to do? Oh, find the angle between F and G. So we have this formula involving the angle here. This formula, which this is actually the same formula you would have had in Calc 3. So it shouldn't be necessarily that hard to get your head around this one because you've seen it before. But it tells us the cosine of the angle. Obviously, if I want to solve for theta, I'll have to get out a calculator and hit the arc cosine button, right, to get the final answer. But in this case, we can just focus more on the cosine of theta. I can see that in order to get the cosine of theta, maybe before I write down the actual cosine of theta, we need to calculate on the top the inner product of the two functions. So that would be the integral from 0 to pi over 2 in this case of sine of x times 2 cosine of x plus 4 dx. Okay, and there's a couple of ways to do this integration. I suppose what I might suggest is to just integrate this part first. Okay, in other words, you can split up the plus sign, distribute that plus sign. So there's a factor of 2. And then when you look at sine of x, cosine of x, that is literally u du, right? The u is the sine of x, the derivative of that is cosine of x. It's literally u times du. So the antiderivative would be u squared, that would be sine squared, all over 2. Okay, and then I would add to that the second part. So I have to do the antiderivative of 4 times the sine of x. The antiderivative of sine of x is actually negative cosine of x. And I take this whole thing and I have to evaluate it from 0 to pi over 2. So we get a little bit of practice with our trig here. So remember your trig values. Guys, if you calculate, well, first of all, this 2 and this 2 cancel. So that's nice. Sine of 0 is 0, so I won't worry about the lower limit here. The sine of pi over 2 is, anybody? It's just 1, right? And I'm squaring that, so it's just 1 squared. And then we have, this is actually a minus 4 times the cosine of pi over 2. I'm just going to write it down. The cosine of pi over 2. So that's the upper limit, right? Maybe I should just, so that's the top limit, and I have to subtract the lower limit. I already said that the sine of 0 is 0. And then here we have, sorry, this is minus 4 times the cosine of 0. So I'm just evaluating the limits, the upper and lower limits of that. Cosine of pi over 2 is actually 0. And cosine of 0 is actually 1. And I have a double negative on that, so it should end up being plus 4. And we have plus 1 at the beginning. So I think if I did it right, it just comes out to 5. Yeah. Look okay? Awesome. So that's the first integral that you have to do. The denominator of our cosine of theta formula involves the norms of the two vectors. So I have to find, the norm of f. Maybe I can squeeze it down here. I have to figure out the norm of f. Now that has a square root in it. Yeah, the square root of the inner product of f with itself. And this one is going to be the square root of, let me just move this over here so I have a little bit more room. Oops. Yeah, so we have to actually do underneath this radical an integral from 0 to pi over 2 of f of x times f of x. In other words, sine squared of x dx. Does anybody know how to do that integral? I'm not going to turn this into a course on integration again, but do you happen to remember it?
Integration by parts.
Don't need to integration by parts. It's something a little bit easier. Josh?
Is it 1 minus cosine 2x over 2?
Okay, use a trig identity. Exactly. That's exactly right. So what I would do here is I would just rewrite sine squared of x as 1 minus cosine of 2x all over 2. Okay. And keep going here for a moment. The 1/2 can be factored out. That denominator is just a number. So I'll pull that out outside of everything. And then I just have to integrate the 1, which gives me x. And then the integral of cosine is sine. So I'll get sine of 2x, but don't forget that by the chain rule, you actually have to put a 1/2 in front of that because it's cosine of 2x. So the antiderivative would be 1/2 of the sine of 2x. And I have to evaluate this one, guys, from 0 to pi over 2. Okay. When you put pi over 2 into the sine of 2x, you just get sine of pi, which is also 0, actually. So both the upper and lower limits here, both the upper and lower limits on this just cancels that term out. It's just literally 0. So the only thing left is pi over 2 with a 1/2 in front of it. So that's pi over 4. And I have to not forget about my radical. So the answer for the norm of f would just be the square root of pi over 4. That seem okay? Yeah, this one, it turns out the computation is slightly messy. We also have to do the norm of g. Is it okay if I write over here, guys? Can you guys see if I move over this side? Okay, great. So this is going to be the square root of the inner product of g with itself. So now I have to take the square root of the integral from 0 to pi over 2 of 2 cosine x plus 4, and that has to be squared. So 2 cosine x plus 4, and that's of course with a quantity squared on it. And so let's square it out underneath that integral sign and also underneath this radical. I'm not doing the integral yet. I just want to FOIL it out basically. So this gives me 4 cosine squared of x. And then when I FOIL this, I should get 16 cosine of x and then plus 16. Okay. Let me just stay up here so everybody can see this. I'll write it way up at the top. So I've got this integral of, okay. I think I'm gonna do this a little in my head, if that's okay. The factor of 4 here, I'm just gonna pull it out of the first integral. And when you integrate the cosine squared of x, you actually get the same thing as when you integrate the sine squared of x, the same exact value. And that was pi over 4. Okay, underneath the radical here, we see a pi over 4 is coming from the integral underneath here, right? So the integral of sine squared of x is pi over 4. Same thing for cosine squared of x. So I'm going to get a pi over 4. And that's because these limits are the same, right? The limits going from 0 to pi over 2. I'm not going to show all my work on that part. You guys don't have to either. If some of you are just now taking the notes on this, that's fine. You don't have to write all that out again. I then have a 16. And again, can I work in my head for a minute? The antiderivative of cosine of x is sine of x. I have to evaluate that from 0 to pi over 2. 1. which gives me 1, right? Because sine of pi over 2 is 1, sine of 0 is 0. Subtract, you just get 1. So it's just 16 times 1. And then finally, we have to integrate the 16 here. From 0 to pi over 2, we're going to pick up a pi over 2 in that. Okay, so we end up with something a little bit messy. The square root of, actually, if you simplify this part right here is just pi. And this part is 8 pi. If I sort of circle those two pieces, pi plus 8 pi, I can just turn that into 9 pi. And I still have a 16 on that. I can't simplify that. I just have to leave it like that. 9 pi plus 16 underneath that radical. Yeah, question?
For the homework assignments, I know for number 4, I use a calculator.
Oh, that's
to,
fine.
like, get a decimal, but can we just leave it like this, let's say on the homework and the exams?
Yeah, that's fine. I actually almost prefer it like this. Yeah, exactly. So the final answer, guys, for the angle would be the arc cosine of, let's see, the inner product of the two vectors. We have to go way back. That was 5, right? 5 on top. And then on the bottom, I have the norm of f, which is radical pi over 4. And the norm of g, which is radical of 9 pi plus 16. There is no need to simplify that. Okay, so you can just leave it in this format. Make sense to everybody? Any questions on that? Go ahead, Kate.
What exam should we try and memorize like trig identities?
The trig identities, this one, oh gosh, I mean, this one comes up so rarely. I would not spend a lot of my time worrying about that. I think this is a great problem for the homework practice. Would I put it on a test? I mean, the problem with that is then I suddenly am, grading people on their trig identities rather than grading them on whether they know the stuff from this class. I don't like questions like that. So if I did something like that and everybody fell flat on their face because I wrote a question about that, that's more on me than it is on you. I wouldn't worry about it too much. Yeah, especially that trig identity. That one is not like the most important trig identity, I think, is, I'm sure you use it in your engineering classes all the time, sine squared plus cosine squared equals 1. That one I can see people probably remember a little bit better, but some of these other ones I'm not quite as worried about. If this was a course on trig, of course that would be the whole focus of it, and I would be expecting everybody to know it, but that's not what we're focusing on for this class. Okay, great. So that took a little bit of work. Number 4 is kind of a long one, even though it's not hard, it's just computationally, a little bit more intensive. Number 8 was another one on the board here. Let me give myself a little bit of room. Number 8 was actually one that I did a little bit in my video, although I didn't fully do it for what they're asking here. Let me explain what I mean by that. So there's about, 4 or so problems where they're giving you a proposal of an inner product and they're asking you, does it work? Is it valid? Meaning, are these 4 axioms true? And so this is one of them. And what they do on this one is they basically give you this formula. So they take 2x2 matrices. So again, we're working in an unfamiliar universe. So they just suppose you have a couple of 2x2 matrices and they propose this inner product formula right here. Okay, at least they spit out a number. It has to be a number, right? When you take the inner product of 2 vectors. But that's a far cry from saying that it's actually an inner product, because we have to check these axioms. Okay. I would definitely recommend going in order on these axioms, because as I was talking about earlier, the first one is sometimes the one that you have to think about that maybe doesn't work. So if I look at the axioms here, guys, this is what problem 8 is just asking you, is this a valid inner product, right? So I go to my first axiom. For the first axiom, I have to put the same vector twice, right? So that just means that I'm going to be putting, let's just call it, I'm going to just call this capital A and I'll call this capital B to save a little writing. right? So I'm just gonna, for the first axiom, I'm just gonna put the same matrix in both spots. And so what the formula would become, if it's the same matrix in both spots, is what? What would I have right here? A11 times A11, right? Which is better known as A11 squared. Okay, so it would just be that. And then the question is, we have to stop and ask ourselves, is that greater than or equal to 0?
We don't know. Oh, we know it is.
We know if we're squaring a number that it is greater than or equal to 0, right? So it is greater than or equal to 0. We'll put a little check on that. Am I done with the first axiom?
No.
Don't forget this second part, guys. It's really a little deceptive. It's like it's like almost like it's another axiom, which is that the only way that we're supposed to be able to get 0 is with the 0 vector. So let's ask ourselves about that. Equals 0 only if, well, obviously this will be equal to 0 only if A11 is 0, right? But does that mean that capital A, which is the original vector, had to be the 0 vector of 2 by 2 matrices? Okay, guys, in the world of 2 by 2 matrices, my 0 vector, I'll write it right here, is this matrix, right? So is that the only matrix that would make this calculation come out to be equal to 0, Vanessa? No, why not?
Just have A11 be 0 and then A122122 be anything else.
Exactly. As long as we make a matrix that has a 0 in the upper left corner, I will already, when I do this calculation, I will get 0. But the matrix, the vector that we started with, doesn't have to be 0. The one I used in the video that you watched was this one. So I actually did this in the video. I'm just repeating it again here, right? So here's an example of a non-zero vector whose inner product with itself still gives me 0. And so that actually fails. So let's just finish this sentence carefully. A equals this has inner product of A with itself equal to 0. So that's bad, right? You have a non-zero vector whose inner product with itself is still 0. And so that just means that this part here fails. This part here fails. Now, is that clear? Is everybody comfortable with that? We've got 30 different people in this room. We could have 30 different matrices here that would all be good examples to use. You don't have to use this example, right? If you all use this example, then my grader will know that you've that I've done this one in class, or that you've watched the videos, which you have. So yeah, but anyway, there's lots of right answers, right? If I want to show that something is false, if somebody makes an assertion and the reality is that that assertion is false, I just need one example to show you that it's actually false. That's all I have to do. So here we go. We have an example. There may be examples where it's true. Like I mean, I could have, this is also an example of a matrix, but this example makes it true. But it doesn't make the whole statement true, right? Like if I say all Saturdays are sunny, right? I can show you a Saturday when it is sunny. That doesn't mean that my statement was true, right? I can give you an example of a Saturday that's sunny, but that doesn't mean it's always going to be. But the statement can be shown to be false with just one example. Just find me one Saturday when it wasn't sunny, and you can say, see, your statement wasn't true. It's not true that all Saturdays are sunny. It's basically the idea we're using here too. Okay, guys, so it's actually game over right now for this inner product. It's not an inner product. And we could stop because we've found an axiom that fails. In this particular exercise, however, the question does have a follow-up. It asks you which of the axioms do work. They want to know what about the other axioms, just to practice them a little bit. Because if we stop after the first axiom, then we're never even going to think about these other axioms. So they do ask you to go on. So they'll ask you, is it true about the second axiom? The second axiom is really just saying, can I switch the A and the B, right? You can see that that's what it is. What do you guys think? Do you think with this formula that I could do that?
Yeah.
Absolutely true, right? So I can write down the formula here. I think you should write this down, right? You should include this in your solution. So when you multiply two numbers together, of course we know, since we were in grade school, that we can switch the order of those. So I can rewrite this one, guys, as B11, A11, no problem at all, right? I can switch those, and then that's just the result of taking the inner product of B first and A second. So something like that would be a beautiful write-up for that second axiom. Okay. Third axiom, same thing. We have a constant times A, inner product with B. So we just look at the same thing again. Remember, guys, when you multiply a matrix by a constant, each slot, so if I have a C right here, it just means that that C goes into every single slot, right? So your upper left corner of your matrix now becomes CA11. So that when you're like evaluating on this side over here, you would have CA11. And so that's exactly what you want to write here. CA11 times B11, right? That upper left corner is now CA11 on the first matrix. And what do I know that I can do with this? Pull out the C, right? Because we're just working with numbers now. With numbers, right? We've known since the beginning of time, right, that numbers can be factored out of a product like that. So we can just pull the C out. And now what I'm looking at in the parentheses is exactly the inner product of A and B again. Okay, so that works beautifully. So all of these are working just fine. Okay. And then the fourth axiom, maybe I'm going to leave that one to you guys. Okay, so for the fourth one, actually, maybe I should say something about the fourth one, because for the fourth one, you need to introduce another matrix. You have to have like 3 vectors there. So let's just write it down. We don't need to skip this right here. So if I wanted to do the fourth one, guys, I actually have to like add another matrix here. So I could do something like this, like A plus X. If you don't use an X, if you use a C or any other letter, it's okay. But this one, right, you literally are going to add these two matrices together. And the upper left corner of that sum is just going to be what? It's just whatever the sum of those two individual upper left-hand corners are. So A11 plus X11, and then all of that is times B11. What's your knee-jerk reaction telling you to do with this? Expand it out, right? These are just numbers, right? When you have just numbers, totally okay to just use your familiar algebra skills, right? A11, B11 plus X11, B11. Just like boil that one out totally. And now you're done, right? This is exactly what you were hoping. You have the inner product of A with B plus the inner product of X with B. Just like that. That's it. So there's really no surprises with the second, third, and fourth axiom, right? Definitely a check mark here, right? This all works just perfectly. Clear enough? I see people taking pictures, totally fine. Just don't print them out and submit them as your homework. Part of what actually, I actually believe that there is some benefit to like actually writing it yourself. So if you've taken a picture of it and then later today you write it yourself, you're actually getting something out of that. So it's totally fine with me to do that. I was kind of joking about sending in the pictures. What's that? I'm tempting you now. Oh, yeah, right. So then my grader sees it and is like, oh, gee, this looks like Dr. Annan's writing. All right. Anyhow, is that good for number 8? Is everybody good on that one? Okay, 17 is up here. Let's look at 17 really quickly. How's my time coming along here? Yeah, let's do 17. And 17, we're back to the vector space of calculus functions from -1 to 0. We're going to use the interval from -1 to 0, and they give you a proposal here. This is their proposal for an inner product, which is that you're going to integrate from -1 to 0. Those are the limits. Oh, so this time they're going to throw an x in here. So x f of x g of x. So that's no longer the standard inner product. That's no longer the standard, like the second most popular example of an inner product. This because we've thrown in this x here, which is not normally what we would do. Okay, if we didn't have the x there, if this x wasn't, then it's already an inner product by Dr. Annan's notes from the video, right? It's like that really familiar example. But if I put this x in here, all bets are off. Now it's like, I don't know. We haven't looked at this one before. We have to think about our axioms. Okay. So they're just asking, is this a valid inner product? So as before, we just have to kind of go through our axioms again. The first one is where you just take the same vector twice in the inner product notation. And this is just going to give me the integral from -1 to 0 of x times f of x squared dx. And the question is asking basically, is that going to be, so I just erased my axioms, but the first axiom is that that should be greater than or equal to 0, always, for every f. What do you guys think? Do you think this would be true for every function?
Yes, because it's squared. So even if it's.
So this part is positive, right? But then we're multiplying it by x. Is x positive or negative, by the way? On this set of limits of integration, you are looking at a part of your number line where x is actually negative. What happens when you take a negative number times something that's definitely positive? You get a negative number. This is not sounding good. This is sounding like a graph that would be below the x-axis. When you calculate an integral of that, it comes out negative. I am suspicious that this is not going to be a valid inner product. So what am I going to do? If somebody comes up to me and says, all Saturdays are sunny, and I'm suspicious that it's not true, what am I going to look for to disprove that statement or to show that it's false? An example, a specific example, right? So I need a function. I need somebody to give me an f of x here. Does anybody have one for me?
2x plus 3.
Let's make it really easy. 2x plus 3 is fine. It would work, but I don't want to have to. I've already had to do 3 hard integrals today. Let's make it really easy. Vanessa, how about just x? Let's just like make this like the world's easiest thing we can think of. Let's try just f of x equals x. Okay, so we're going to integrate from -1 to 0 of x times x times x, right? That's just x cubed, right? And now this becomes 1/4 of x to the 4th. All right, we're evaluating it from -1 to 0. Let's just see what happens here. When I plug in the top limit, I get 0, right? 0 to the 4th. And then I have to subtract the lower limit. The lower limit gives me, well, -1 raised to the 4th is just 1. So it's literally just -1/4. And that, my friends, is less than 0, which violates the first axiom of an inner product, right? So we can now say that this one fails. Just like before, this one fails. So it is game over here. Okay. That makes some sense? Oops, sorry. Now, on this particular problem, I don't think they're asking you to go on. I think it just says, is this a valid inner product? Show why or why not. We've got an axiom that fails, so we're done. We don't have to check the other axioms. So I think, again, if you wanted to for your own practice, you could do that. And I think the other 3 axioms, again, would work. So it's really this first axiom that's kind of the hang up here. So, okay, great. I have exhausted the problems that are on the board so far, but I'm gonna give you another chance because we're gonna take a break soon. And during the break, if you think of anything else that maybe would be good to look at, we can do that. But for the moment, let's put the homework aside because I would like to talk to you guys about another section of the book here. So this is gonna be 5.2. We're gonna take some notes now, if that's okay. We'll take a few notes for a few minutes and then during our break, we'll see if we can get some more problems on the board. Totally okay with that. Okay, so, and to kind of lead into this conversation, I'm gonna put this angle up here again, so that I accidentally got this thing erased already. The angle between the vectors x and y is just the inner product of x and y divided by the norm of x and the norm of y. We're gonna need that. We're gonna need that. So this next section of the book here, 5.2, this is about orthogonal. I'm gonna put slash orthonormal sets. Orthogonal and orthonormal sets of vectors is really what we're talking about. And so let me write down a definition for you. So here's a definition to kind of kick off this little section. This is a short section. That's why I'm diving into it right now. It won't take us too long to cover this. Non-zero vectors. Non-zero vectors V and W are orthogonal. They are orthogonal. And by the way, I sometimes write that, you'll see people write it this way for orthogonal. They'll kind of draw it like a T, upside down T, like it's an intersection of streets or something. And the reason that they draw it like that, by the way, is because they're trying to emphasize that you have some kind of a right angle. It should be a right angle. What's the degree measure of a right angle? 90 degrees, right? What is the cosine of 90 degrees?
1.
Careful. Cosine of 90 is actually 0. Okay. Don't worry, you don't need to know that, except I think on the first homework for tonight, the very first problem, number 1, I think you have to know that. Anyway, so the answer is cosine of 90 degrees is 0. 0, yes. I'm gonna confuse myself. Well, if this is equal to 0, guys, if this is equal to 0, you can clearly see how that would happen, would be that this numerator was 0. 0 divided by something, that would be 0, right? So the definition that we're going to put here is that the inner product of V and W needs to be 0. So two vectors are orthogonal if their inner product is 0. And just to extend that definition a little bit, I could have a whole set of vectors that are all mutually orthogonal to each other. So let's just say that a set, another definition, a set S, which maybe has vectors V1, V2, and so on up to Vn, is orthogonal. So we can talk about not just two vectors being orthogonal, but a whole collection of vectors in a set S. The whole set S can be orthogonal if, well, this is kind of the natural thing to have here. The inner product of Vi with Vj is equal to 0 for all I not equal to j. So for all I values that are not equal to j, so any two of the vectors would be like mutually orthogonal. By the way, orthogonal is just a fancy word for perpendicular, right? These two vectors are perpendicular. In R2 and in R3, right, in our physical world, we kind of know what perpendicular means, but now I'm kind of pushing the envelope. I'm like saying, I want to talk about two functions being perpendicular. I want to talk about two matrices being perpendicular. I want to talk about two polynomials being perpendicular. if I'm in an inner product space, I now have a definition for that idea. Okay, it actually does get used. This isn't just like playing games right now, right? In the real world, this stuff is quite important, particularly to engineering. So we have this definition, and also if in addition, the norm of each one of my vectors, so this is the norm of v sub I, if it is equal to 1 for each I. Does anybody remember from my video what we call a vector that has a norm or a length of 1?
Unit vector.
It's a unit vector, right? You probably use that word in Calc 3 as well, right? So a unit vector is just one that has a length of 1 or a norm of 1. If that's true, so if your vectors are all mutually orthogonal, and if they are all unit vectors, then we actually have an even stronger idea. We call S orthonormal. Okay. So a set of vectors can be actually orthonormal if it's both orthogonal as a set to begin with, and all of the vectors are actually unit vectors. So let's just do a quick example here to make sure we understand that definition. Back over here for a minute. Quick example. Okay, so for the example, let's take vectors in R4. So V is equal to R4. Right away, if I'm doing vectors in R4, then I don't have pictures. I cannot visualize four-dimensional space here, but we can still ask whether some vectors in that space are orthogonal or not. So here is the question. I'm going to give you a set S, which is going to be the vector 3, 1, 5, 2, and then 0, 6, -2, 2, and then -2, 3, 3, and -6. And I'm going to ask, is S an orthogonal set? Now, is there anything missing from this question that probably we should have been told, Don? We don't have to have 4 vectors, so these are definitely, okay, I know where you're going with that thought. Could these possibly be a basis for R4? No chance, right? How many vectors would you have to have for a basis for R4? You'd have to have 4. I only gave you 3. They cannot possibly span R4. So they're not a basis, but that's not really the question here. The question is whether they form an orthogonal set or not. And am I missing something that if we're in chapter 5 and somebody gives us just a vector space, what else do we have to know about if we want to be able to play with all the ideas in this chapter? An who said that? Inner product formula. We have to have an inner product formula, right? They didn't give it to us. So I think in my video from a week ago, I talked about this, right? If we have just Rn, and if they don't tell us what inner product formula to use, then we should assume, even though it's not stated, we should assume the usual dot product. Guys, they have to tell you the inner product formula. If you are not given a formula for how to do the inner product of 2 vectors, then you're kind of screwed as far as doing anything in this chapter, right? We have to have that formula. We have to have that formula. Okay, so we're going to use the usual dot product, right? So let's just label these vectors here, guys, V1, V2, and V3. And to check if they are forming an orthogonal set, I just have to check every possible VI, VJ combination, right? So this is actually pretty easy. You're going to be doing this for the next homework assignment. You just have to like calculate this, the inner product of V1 with V2. And then we're going to do the inner product of V1 with V3. And then we're going to do the inner product of V2 with V3. Like we're going to do every combination here. Every combination of putting two of those vectors together. Okay. So for the inner product of V1 and V2, I'm just doing regular dot products, guys. So let's just do this quickly if we can. Regular dot products, 0 plus 6 minus 10 plus 4, right? 0 plus 6 minus 10 plus 4, that adds up to 0. You don't really have to show any work. It's kind of just in your head, we can calculate these things. V1 and V3, let's take a look at the first one and the third one. -6 plus 3 plus 15 minus 12. Everybody see what I'm doing? Dot product, right? Dot product. So -6 plus 3 plus 15 minus 12, that's also 0. Okay. Just put a little check on that. And then finally, V2 and V3, 0 plus 18 minus 6 minus 12. 0. Right. So they're all canceling out. Everything cancels out. Every mutual pair of vectors has an inner product of 0. So the answer here is yes, they are an orthogonal set. Clear enough? Now, as a follow-up, let me ask you a quick follow-up here. Are they, so is S orthonormal? So if it's orthogonal, then the natural next step would be to ask whether it's orthonormal. So let's go back to the definition here. To be orthonormal, in addition, the norm of every vector has to be 1. So to answer this question here, I have to start calculating, well, what is the norm of V1 and what is the, I'll just do all three since I'm here, right? I'll just check these. The norms of these vectors would have to be 1. So if I do the norm of V1, remember what that is. That's the radical of the inner product of, oh, here, I don't need this much room. It's just the radical of the inner product of V1 with itself, right? That's the definition of the norm. That's what the norm means. And how do I calculate that then? Well, I'm just taking the dot product of V1 with itself, right? So I look back to my first vector, I'm just going to dot it with itself. 3 times 3 plus 1 times 1 plus 5 times 5 plus 2 times 2. That's the dot product of this vector with itself, slot by slot. So that's 9 plus 1 plus 25 plus 4. 39, right? So this is actually, let's just write it out though. 1 times 3 squared plus 1 squared plus 5 squared plus 2 squared. It's radical 39. And so can we answer our follow-up question already?
Yes.
Is it an orthonormal set? No chance, right? It's got a vector. Even if these other two vectors had a norm of 1, it's not orthonormal because if even one vector is not a unit vector, it's game over, right? It's not going to work. So I can already put a no here. It is orthogonal, but it's not orthonormal. Okay. I will let you guys check these other ones. The norm of V2 turns out to be radical 44, and the norm of V3 turns out to be 58. Square root of 58, yeah. So actually, none of these vectors are actually unit vectors. So I do have one more follow-up to this question, though, is, all right, it's not an orthonormal set. Could I make it into an orthonormal set? Okay, I'll just put that here as another follow-up. I'll put this one in blue. Can we make S into an orthonormal set. It's not orthonormal to begin with because the vectors don't have a norm of 1. But is there something we could do that would allow us to turn it into an orthonormal set? Have we done this ever in calculus? EROs would be a totally different situation where we have to have a matrix, right? So I'm thinking more just of Calc 3. You have a vector that's not a unit vector. Is there a way to take a vector and without like totally screwing it up, to turn it into a unit vector?
Find the whole thing very small.
Exactly. If you take a vector and you scale it down by dividing by its norm, yeah, it becomes a unit vector then. Right, so the answer here is yes. By the word I like to use for this is we're going to do this by normalizing. We're going to be normalizing each vector. I talked about this in my video as well that you guys would have watched back the sort of the intro video for chapter 5. If you have a vector that's not a unit vector, it'll become a unit vector if you simply divide by its norm. And so what we would get then for our set would be, I'll write it as a set here, 1 over radical 39 times the first vector there, which was 3, 1, 5, 2. Okay, so that's normalizing that vector. We're literally shrinking it down by dividing by its length so that it has a length of 1. Now I'm going to do that with each of my vectors. So the second one would be 1 over radical 44 times whatever the second vector was, 0, 6, -2, and 2. Guys, let me know if you can't see this. If this isn't showing up clear for you, let me know. But I'm just taking the original 3 vectors and normalizing them, right? For the third vector, I have to divide by the radical of 58. That's the same idea, right? -2, 3, 3, and -6. Now this is an orthonormal set. So now we could, at this point, we would say, yes, that is an orthonormal set at this point. Very good. Okay. Everybody hanging in there? Awesome. This isn't too bad, right? Now, of course, remember, we can do all this stuff not just with nice vectors with slots and with the regular dot product. We can do this with any vectors with any inner product. So there'll be some practice for you to do that in section 5.2. We just have to use the given formula for how to do the inner product, and we can do all of this process again. So it's not anything too crazy. So I'm just erasing it now. We have the idea of an orthogonal set. Then we have the idea of an orthonormal set. I can actually now take both of those concepts and apply them to a basis. An orthogonal basis for a vector space. It's just a basis consisting of orthogonal set. An orthonormal basis is just a basis consisting of an orthonormal set. So you see, we can combine these definitions of orthogonal and orthonormal into the realm of bases as well. I know I've been talking for a while, but I'm going to do one more example and then we'll take a break. Does that sound like a fair game plan? Let's do it. So one more example here. So I'm just going to first of all make this definition. I just stated it verbally, but I'd like to write it down too, which is just that an orthogonal, one more definition, orthogonal, and in parentheses, I'm going to also at the same moment talk about orthonormal basis for V. An orthogonal or orthonormal basis for V is a basis that forms, is a basis that forms an orthogonal slash orthonormal set. Pretty simple. It's just basically It has to be a basis and it has to form an orthonormal, orthogonal or orthonormal set, depending on which word we're working on. So let's do an example of that and then we'll stretch our legs for a minute. Okay, so here's a quick example. I am going to take V to be P1 of R. So we're going to do a polynomial example right now. These are polynomials of degree 1 or less. So they would have the form AX plus B. Any polynomial of the form AX plus B, right? And then what I'm going to do is I'm going to ask us to show that S, which consists of just 1 itself, this is not the number 1. This is not the number 1. This is the polynomial 1. So it's like f of x equals 1. It would be a flat graph, 1 unit above the x-axis, all the way across from minus infinity to positive infinity. So that's my first polynomial. And my second polynomial is radical 3 times 2x minus 1. Show that that set is an orthonormal basis for V. Let's try to show that that set is an orthonormal basis for V. And while I'm erasing over here on the left side, I want you guys to think about what information is missing from that question, because that question, as stated right now, does not make sense. Yeah, so show that this is an orthonormal basis for V, but the word orthonormal is in there. That means we must be in chapter 5, right? We're not just in a vector space, we're in an inner product space. What's missing from this problem statement? The formula for the inner product. Now, guys, if it was Rn and I made that omission, you're supposed to assume it's the regular dot product, because that's so standard as people don't even bother to mention it, right? So for Rn, which is just vectors with slots, if they don't tell you what inner product formula to use, I said this a few minutes ago, I'm just repeating it again, you will always just use the regular dot product in that case. But this is not Rn, right? This is some other universe. In any other universe, there is no go-to formula that everybody just immediately gravitates to. We don't know the formula, so somebody better tell us the formula. So here, to make this more clear, we're going to add to the question just a little bit of clarity to it. Use the inner product of f and g is the integral from 0 to 1 of f of x, g of x, dx. So we won't stop right now, and we don't have to stop and verify that that's an inner product. We can just use it. Okay, so that has to be given. This part in the brackets, totally required, or it doesn't even make sense. Okay, so I would like to start off with, for the solution, just solve this one, guys, then we'll take a little break. For the solution, I'd like to start off with explaining why it is even a basis at all. Let's not worry about the orthonormal part of it yet, the new material. Let's go back to chapter 4. This is a good review. I would like to understand why these two vectors form a basis for P1 of R. Remember, to be a basis, they have to be a spanning set and they have to be Li. Is there anybody who could address either one of those two issues just at a glance? Josh.
With the dimension equals number of vectors, you know that it's going to be both needed.
Okay, beautiful. So Josh is pointing out that we actually know the dimension of V. By the way, what is that dimension? The dimension of Pn of R is always n plus 1, right? We add 1, so in this case it would be 2. And in this case, K, remember the variable I was using to count how many vectors I have? The number of vectors in S, 1, 2, right? 2. Oh, they match. They match. The K matches the dimension of V. We just did this on the homework recently, right? When that happens, that means S is both or neither. It's both or neither. Of course, we want it to be both. That's what we're claiming is it's a basis. So can somebody tell me why either they can tell just by looking at it that the vectors would span V, or just by looking at it why they would be Li? Because we need to explain at least one of those. Go ahead, Jared.
Well, you can't get an X from just one, so.
Okay, the question is, for two vectors, are these scalar multiples of each other? Can I take one and multiply it by a number and get this guy? And Jared's point is absolutely spot on, which is no, you cannot do that. These two vectors are not scalar multiples of each other. And when you have only two vectors, that's enough to be able to just say right away that they are Li. Right? So I'm just going to write that down. S is Li since the given vectors are not scalar multiples of each other. So it's both or neither. And since it's a thumbs up on the Li part, it has to be a thumbs up on the spanning part too. We don't even have to address the spanning part. It's automatically going to come with the territory because it's both or neither, and it is Li. Guys, by the way, guys, be very cautious not to use this scalar multiples trick if it's more than two vectors. I can very easily give you three vectors. These are just vectors in R2. These three vectors, no two of those are multiples of each other. But if I have three vectors in a two-dimensional space, we know they are LD. Okay, so even though there's no scalar multiples here either, this is bad. In fact, I can see the third vector is just the first one plus the second one, which means there's a linear dependency there, right? So this idea of not scalar multiples of each other works great when you only have two vectors. Okay, just reviewing, this is all just from chapter 4. Okay, so thus S is both. I'll just say thus S is a basis for V. So we have a basis. Excellent. We have a basis. This is a good first step. We have a basis here. But we want to show that we have an orthonormal basis. So I have a little bit of more work to do. Once I have a basis, now I've got to check, is it orthogonal? Okay, so let's do that. And then we also have to check if it's orthonormal as well. So check orthogonal. I'll do that right here. I'll do this one right here. So for orthogonal, remember what that means? That just means the inner product of the two vectors should be 0, right? Should be 0. So I'm going to take the inner product of 1 with radical 3 of 2x minus 1. This means I have to take the integral, because I have the formula now. They gave me the formula, the integral from 0 to 1 of f of x times g of x. So it's radical 3 times 2x minus 1 dx. Okay, so we just have to work this one out. And the radical 3 can pull right out of my integral, right? Put that out in front. And then when I integrate 2x, I get x squared. And when I integrate 1, I get x. So I'm just doing the antiderivative here. And I will evaluate it in a moment from 0 to 1. Okay, the antiderivative of 2x is just x squared. The antiderivative of 1 is just x. Subtract the 2 and evaluate. So if I plug in 1 for x, I just get 1 minus 1. That's 0. When I plug in 0 for x, I just get 0 minus 0. That's 0. The whole thing is just 0. Check it off. That's good. These vectors are orthogonal. Okay. Let's check the orthonormal part. I only have 2 vectors, so I don't have anything else to check for the orthogonal piece. It's just that right there. So I have to check that these vectors, not only are they mutually perpendicular, I also want to know that they are both unit vectors, right? Both have a norm of 1. So I'm going to check the norm of 1 right now. Let's write this very carefully. This is the radical of the inner product of 1 with itself. That's the definition of the norm, the square root of the inner product of the vector with itself. And now underneath that square root, I have to evaluate this, this inner product. So I'm going to go integration from 0 to 1 of, well, f of x times g of x is just literally 1 times dx. Do I need that much of a space for this? And so you're just literally integrating dx. And well, when you integrate dx, you just get x from 0 to 1. So underneath that radical, you're just evaluating x from 0 to 1. And when I plug in my upper limit and lower limit and subtract, I just get 1 minus 0, which is 1. So there you have it. We have a unit vector for that first vector. Just like that. Okay. I also have to do the other vector. We have to check both of them. The norm of radical 3 times 2x minus 1. We have to check this one as well. This one's a little messier, but it's not that bad, right? So this is going to be, again, the radical of, I'm just going to go straight to the integration, if you don't mind. It'll be the integral from 0 to 1 of this thing times itself, right? Radical 3 times 2x minus 1 times radical 3 times 2x minus 1. Well, that's just 3 times 2x minus 1 squared dx. This is literally what it would be. So I've got to work underneath this radical. This is getting a little messy. I'll pull the 3 outside. And then, actually, if I was willing to throw a 2 in there, I want to think of this as u squared. I would like to integrate just u squared, but of course the du of that would have been 2 dx. I don't have a 2 there, so I can put a 2 in there. I'm just going to cheat right now, guys. I'm going to put a 2 in there. It costs me a 1/2. So I pull the 1/2 out when I get to the next step of the process. So I'm just doing this integration as a u substitution. So u is equal to 2x minus 1 and du is 2 dx, right? So I've got my 2 dx right there. I've got my u right there. It's just u squared du. And the antiderivative of that would be u cubed, which is 2x minus 1 cubed over 3. Just like that. And I've got to evaluate that one also from 0 to 1. Okay. That okay with everybody? I went a little quick through that. That's just literally a u substitution. So now I've got to cancel the 3's. And what do I have? I have radical of, there's still a 1/2 in front. When I put in 1 for x, I'm going to get 2 minus 1, which is 1 cubed. And then I have to subtract the lower limit, which is 1/2 times, when I put in 0 for x, I actually get negative 1 cubed. And negative 1 cubed is actually minus 1. So it turns it into 1/2 plus 1/2 underneath that radical, right? So if I did my math right, it's 1/2 plus 1/2 underneath the radical. So that adds up to 1, and square root of 1 is 1 again. So it works again. It's all good. Yeah, question.
If the question asks for orthonormal, how come we have to check if it's orthogonal?
So part of the definition of a question was, if I know that my vectors are supposed to be orthonormal, why do I have to check orthogonal? It's because the definition of orthogonal vectors is that they are first the definition of orthonormal set is that they must first be orthogonal.
Oh, okay.
So we actually have to check that part first.
Okay.
And then we can check the norms here. So this is the reason that this radical 3 was actually put in. And you might have wondered when we started the problem, why did they put a radical 3 in there randomly? Oh, it's exactly to make this calculation with these 3's canceling. It's just to make that work out perfectly so that they are in fact unit vectors. Yeah, it wouldn't have worked otherwise. Oh, by the way, guys, if I change the limits of integration here, If I do something like that, even this won't be a unit vector anymore. Right, even though it looks like it's a 1, well, shouldn't that be a unit vector? Well, you can see if I change this limit of integration to a 2 and I try to do this, it wouldn't work anymore, right? I hope you're not writing that down. I'm just trying to show you how important the inner product is. I tweak this inner product formula, suddenly all hell breaks loose, right? Now everything that was true before is no longer true. That's kind of something you got to be careful about. Yeah, man.
So if it wasn't orthonormal before, we could make it orthonormal?
That is true. So if like if we work this out and it was a radical 2 here,
Yeah.
well, so what would I do then? What I would do is I would say, okay, I'm going to divide by the norm to make it into a unit vector. So we could still do that normalization process, just as exactly like we did in the last example. Great question. Fabiola.
So you have to use the integral because that was the equation given to you?
Exactly. Somebody has to give us this formula. Otherwise, we're sort of standing there wondering, what are we supposed to do? Right? You have to have that formula.
Could it have been a different formula?
If I change this formula to integral from 0 to 2, now these two vectors don't work anymore as an orthonormal basis. Or I could have changed it completely into something that wasn't even integration.
Yeah, I was gonna ask you to do something that wasn't an integral.
Yeah, you anything that satisfies those 4 axioms is something that would be a legitimate inner product. So there could be the floodgates are wide open on what it could be. However, these integration types of expressions are the most common ones that we see. Good question. Great questions. Yeah, Adrian.
If given that basis or inner product should be tested just in case it's like.
Oh, no, so like on an exam or something,
Yeah.
if I give you an inner product formula, unless the question says, please verify if this is an inner product or not. If it's anything else, like a problem like this, if I hand you that inner product and I start asking you geometry questions or things about orthogonal, orthonormal sets, you can take it on faith that I've given you a good, legitimate formula. Yeah. So it's really tonight's homework where we're verifying those axioms. The problems you're going to do for Thursday, which are kind of based on this stuff, you're going to just take the inner product formula and run with it. You're just going to test for orthogonality, orthonormality. You're not even going to think about whether the axioms are true anymore. Good question. Yeah, Jonathan.
So if it's not orthonormal, we can make it orthonormal.
Correct.
If it's not orthogonal, we can't make it.
If it's not orthogonal, you just brought up a really good question. If my vectors are not orthogonal to begin with, can I make them orthogonal? Because we just had this great idea for taking vectors that are not orthonormal and turning them into orthonormal vectors. Turns out we have a process called the Gram-Schmidt process that we can use to do that with. So that's actually in the next section. So good question. It's right around the corner. Okay, guys, let's take, it's already 3:28. I went really long there. Sorry about that. Let's take just a 5-minute break today. I want to try to save a few minutes so I can do a few more things. During this 5-minute break, if you want to add anything else to this list over here, we can try and do it. I don't promise I'm going to cover everything that gets up on this board, but we can take 5 minutes and write something down if you want. So make a real quick trip to the restroom or to the outside fresh air. And in about 5 minutes, we're going to start up again. All right, guys, I think I'm gonna go ahead and pick things back up. That turned into more like an 8-minute break, but that's okay. I only have like 15 minutes. I am gonna try in 10 minutes to explain section 5.3. It's a really quick one. If I don't quite get a chance to do a full-blown set of examples, I might send you a little video that's just got a couple examples and it's real short. But in the meantime, let's see what I can do. I want to get back to what Jonathan was just asking right before the break, which was, if we had a set of vectors that were not orthogonal to begin with, could we orthogonalize them? Could we make them into an orthogonal set? Okay, so I would like to talk about that. There is a way to do this, and so I'm going to put a little diagram up here for you guys. And on the first part of this diagram, I'm going to write orthogonalize, okay? So we're going to try to orthogonalize those vectors. And this is the part I have to explain. The new vectors that you get, which are W1, W2, up to Wn, right? So we take this original basis, excuse me, which has V1 through Vn. We're going to do something to orthogonalize it so that it becomes what is called an orthogonal basis for V. Okay. So those are going to be denoted with W1, W2, up through Wn. Okay. And then maybe that's all that we want. Maybe we just want to have an orthogonal set. If we do, we can stop at the end of whatever that process is that I'm going to talk about. On the other hand, it might be that they will ask us to go even further. This is perhaps optional. We might not be asked this part, but we might be asked to normalize those vectors as well. And if we normalize our already orthogonal set, we will get what I will denote with U1, U2, and ... up to UN, because those are now going to be unit vectors. And this now becomes an orthonormal basis for V, right? So we can create an orthonormal basis for V if that's what they ask us for. Now, the right-hand side of the picture, we already know how to do that, right? We know how to normalize. We've already been doing it today. U sub I is literally just take W sub I and divide by its norm, right? So we know that even from Calc 3, right, that we've had to do this kind of a thing before. We take a vector, we shrink it down so that it's a unit vector. So this is the normalization process. By the way, Enrique, after class, can you come up here? Because I have something for you. Thank you. So I just saw you and just remembered I need to do that. Right, so the right-hand side of the picture is easy to handle, but this left side is the part we don't know how to do yet. How do we take a set of vectors and orthogonalize them? This is something called the Gram-Schmidt process. The Gram-Schmidt process, there was two mathematicians that sort of discovered this. They both get credit for it in the name of this process. It's going to be called the Gram-Schmidt process, and that is actually really the title of section 5.3. So Gram-Schmidt process, this is how we take any basis whatsoever or any vectors whatsoever and orthogonalize them. This is the idea. Okay, so I have to explain this Gram-Schmidt process to you. Okay, well, let me actually give you a couple pieces of good news about the process. The first one is I will not ask you to do this Gram-Schmidt process for more than 3 vectors. So on the homework, on the midterm review materials, and on the midterm itself, I will never ask you to do this for more than 3 vectors. That's the first bit of good news. The second bit of good news is that I'm actually going to tell you the formulas for W1, W2, W3, and I'm going to put them on the test. So you actually will not have to learn these at all, okay? How is it going to work? So for the Gram-Schmidt process, I'm actually going to write down the formulas now. And again, these will appear on the midterm. You do not have to memorize these, but I'll tell you what they are. The first one is W1, and it is equal to V1. I mean, after all, the first vector, if you're just starting from the beginning and you write down the first vector, well, it's already, there's nothing for it to be orthogonal to yet. So let's just leave it the same. Okay. For W2, the way you calculate W2 is, and again, I will be giving you this formula. You do not have to memorize these formulas that I'm writing down right here. We start with V2, and we are going to subtract off the part of V2 that is sort of pointing along V1. Because I want to kind of make this thing orthogonal to V1, right? W2 should be orthogonal to W1. And W1 is V1. So I want W2 to be orthogonal to V1. So I'm going to subtract something off of the second vector so that it becomes orthogonal to V1. And what do we subtract off? Well, this takes a little derivation, which I may postpone until Thursday. But essentially, you take the inner product of V2 with W1, and you divide by the norm of W1 squared, and then multiply by W1. Okay, so it's kind of messy. I'm not going to expect you to memorize that. It's actually pretty easy to actually use this formula if you're getting good at inner products, because you're just calculating an inner product. You're taking a norm. By the way, the norm of a vector squared, I think everybody probably realizes this, but just to be sure, that's literally just the inner product of the vector with itself. The radical is no longer on it because I've squared the norm. All right. So that's really what you have here. You have the square of the norm of W1. Guys, this whole fraction here in front is just a number, right? This is just a number. The V2 inner product with W1, that's a number. The norm of a vector is just a number. This is literally just a number, some scalar multiple of W1 being subtracted from V2. It's actually very easy to show you this with a picture, actually. So here's V1, and here's V2, right? So V1 is going to just become W1 according to my formula here. We leave that one alone. And now for the second vector, what I'm going to do is I'm going to replace V2, guys. I'm going to replace V2 with a vector that is is this the right way? Oh, you know what? Can I change my picture? Are you guys drawing this picture? It'll be better for the purposes of the way I've drawn this. Let's get rid of this here. Sorry. Getting too excited. Let's put the V1 on the bottom. It'll just look better. Okay, it just makes the picture look better. So this is just W1, right? V1 and W1 are the same. So I come along with that second vector V2. What I want to do is replace it with W2. And I want W2 to be orthogonal to W1. What I'm going to do, guys, is I'm going to replace V2 with W2. How am I going to do that? Well, I'm actually literally going to do vector subtraction, and I'm going to subtract. I'm going to take V2 and I'm going to subtract. Guys, just look at the triangle. I'm going to take V2 and I'm going to subtract this lower leg of the triangle, leaving me the blue part. That leaves me the blue part. I take V2, I subtract. What is this, by the way? This is some scalar multiple of W1. Well, that's exactly what this little arrow looks like, right? Here's the whole W1, right? Here's some scalar multiple of W1. A derivation, which I might show you on Thursday, will show you that this is the right coefficient, the right scalar in front. We subtract that off, it leaves me with W2, and W2 is now orthogonal to W1. Okay, and then finally, we have to do the same thing for to get W3. So W3 is V3 minus the inner product of V3 with W1 divided by the norm of W1 squared times W1. So just like before. But then we now have to also subtract a scalar multiple of W2. So we'll take the inner product of V3 with W2 divided by the norm of W2 squared times W2. These three vectors, and there could be more than three in the real world, but at least for the purposes of a handwritten Math 250B exam, I will not give you more than three. These three vectors now form an orthogonal set. Okay. And I'm going to give you these formulas. So these will be given. Matt, did you have a question?
Yeah, if there are more vectors, then it just keeps following that pattern.
It does. Yeah, if there was a W4, we would have a V4. We would subtract 3 terms. Exactly. They just keep following that pattern. So I'm going to give you those formulas. You don't have to memorize them. This is one of the least conceptually challenging sections of the whole entire book. You basically have the formulas and you run and play with them. The computations can be messy. I will not lie to you about that. You can get numbers in these fractions, and you have fractions being subtracted from things. That can be a little bit messy. So, but the theory of it is pretty simple. So I want to take the short little bit of time I have left today to talk about a couple more homework problems. So what I'm going to do is send you guys a little video clip. I promise it's really short. Yeah, I think it's less than 10 minutes to just watch me solve 2 examples of this Gram-Schmidt process. Are there any questions on it? So far, so good. Okay, great. Because I want you to be able to get this homework that's due tonight done relatively easily. So we only have 3 minutes, but I only need 3 minutes to do these 2 problems. They're both fast. They're both proofs, but I'm going to do 30 and 31 right now, and then probably with 12 I might run out of time. But let's see how I can do on number 30, which is this problem right here. Sorry, I'm making you dizzy with all the shuffling from the lecture to the homework to the lecture to the homework. Back to the homework again, guys. There's this problem. They're asking you to prove that if I take the inner product of U with V plus W, notice that the plus sign is in the second slot. If we remember our list of axioms, the fourth axiom has a plus sign in it, but it's in the first slot. So does anybody have a suggestion how we could work with an expression where the plus sign is in the second slot? Matt?
Oh, you use the second axiom.
The second axiom, right? This, I know I don't have them on the board right now. But the second axiom allows me to switch the order, right? So guys, this is what you need to do for problem number 30. It's very short. We're just gonna switch the order. It would be good to tell me which axiom you're using. So by axiom 2. Once I've got them switched, what can I now do with that expression that I couldn't do before? Distribute it out. What's the reason for that one? Axiom 4, exactly. So by axiom 4, I can split this one out, right? This is one of my axioms of an inner product. So I can split that one out. And it's not quite what I'm trying to get to at the end, but what do I need to do if I want to get from here down to here? Back to axiom 2 again. Just switch them back again, and then you're done. That's the whole problem. So you're allowed to switch the plus sign to the second slot. Okay. And then finally, problem 31 is along the same lines. 31 is asking you to write an expression for this. The inner product of u plus v, comma, w plus x. Okay, so they're asking you to come up with a formula for that. And at the end of the day, the answer is going to be that you can literally like FOIL this out into 4 terms. But let's do it just one at a time. Let's use axiom 4. Okay, slow me down if I'm going too fast. I'm just excited. I've got this plus sign here, right? I can split that apart. So I can write this as the inner product of u with w plus x plus the inner product of v, comma, w plus x. Right? I can just split the first slot. Now guys, the truth of the matter is, after I'm done doing this homework problem, we don't ever have to go through this set of steps again. We just FOIL it out from now on, right? But just for this one moment, we have to do it this way. And now what am I going to do next? I could use axiom 2, but is there something faster now? We just did problem 30, right? Which allows us to split up a plus sign out of the second slot. So I'm going to now say by number 30, it would not be wrong to use axiom 2, but then we would be like reinventing the wheel again, right? We may as well just use problem 30, which says, yeah, you can totally bust the second slot apart as well. U comma W plus U comma X plus V comma W plus V comma X. That's the whole thing, right? And that's actually the answer. So this is problem number 31. We're done with it. Everybody get out your cameras. Yeah, that's all you have to do for that. Does that make sense? Okay, I ran out of time for number 12. I'm sorry about that. I do have office hours after 5:30 today, so feel free to do that. And I know I've got another assignment for you for Thursday. It's based on the stuff we just covered today. Do your best with that, but you know what we'll do on Thursday? Take more questions on more homework again. So I will help you with that as well. Thanks for a great day, guys. I look forward to seeing you all again really soon.